high-performance domain-specific compilation without domain-specific compilers. And let me begin with saying a few words about myself. So I'm a fourth-year PhD student from the University of Münster in Germany, and I just submitted my PhD thesis. So this is kind of a summary of what I've been doing for the past 4 years. So let me begin with asking the question, what high-performance domain-specific compilation actually is and why I think we want it. And specific compilation is a solution to the following problem, where we, on the one side, have domain scientists who require some high performance for scientific applications, such as training a large neural network. And on the other side of that gap, we have modern parallel hardware, which is theoretically capable of providing that high performance, but only if it's programmed in the right way, which is typically not in the expertise of the domain scientist. And domain-specific compilation now bridges that gap with a domain-specific compiler, which provides high-level abstractions to the domain scientist and automatically generates code that is optimized for a particular hardware architecture. Now, if this is a solved problem, then why are we trying to achieve this without domain-specific compilers? So what is wrong with them? And the problem with domain-specific compilers is that they are not reusable, and this kind of almost by definition. So a domain-specific compiler is specific for one particular application domain, and it is often only targeting one particular hardware architecture. And if you now take into account all the different application domains we have and all the potential hardware architectures we might want to target, I guess it's no surprise that we see this kind of explosion of domain-specific compilers being developed today. And since there's little to no reuse between the implementations of those compilers, we always have to start from scratch, which is very time intensive. So what I've been thinking about a lot in the past 4 years is how can we design a reusable domain-specific compiler? And for this, we have to answer two main questions. And the first one is, how do we represent domain-specific computations in the compiler internal IR? And the second is, how do we encode and apply domain-specific optimizations? And yeah, this is what I've been doing for the past 4 years. And in this talk, I will give a brief teaser to my latest work, which is joint work with colleagues from the University of Glasgow and Edinburgh. And it's called Achieving High Performance the Functional Way, and that will be presented next week at ICFP. And before I introduce you the functional way of achieving high performance, I will briefly want to explain the current way of achieving high performance using domain-specific compilers. And there's one particular approach very popular in domain-specific compilers these days, and that's called schedule-based compilation. And the concept of that is what you see here. And on the one hand, we have the domain scientist who uses some high-level API to describe the computation in a so-called algorithm. So here, for example, we see the TVM compiler who provides a high-level Python API to the domain scientist, which can be used to, for example, describe a matrix multiplication, which you see on top. And then separate from that, we have a performance engineer who writes a so-called schedule, which explains how to optimize that matrix multiplication for a particular architecture. And that is the program you see on the bottom. And the idea is that you can now provide different schedules for the same algorithm to optimize it in a different way. And the TVM compiler comes with a tutorial on which explains to you how to use that scheduling language and how to develop 7 different versions, which eventually leads you then to a 200x speed up compared to the initial version of matrix multiplication. And this is, as I said, a kind of popular approach of achieving high performance in domain-specific compilation. But if you look a bit more closely at that approach, we see a few problems. And so one of the first things you might see is that the separation between algorithm and schedule is kind of blurred because both use the same identifiers, which means they have to live in the same scope, which then means that it hinders reuse, that we cannot simply use the same schedule for optimizing a different algorithm. And another problem is that the optimization primitives this language exposes does not have a well-defined semantics, but only kind of some rough documentation, which hinders understanding, because in order to know what's going on, you need to have a detailed knowledge of how the compiler implements it internally. And the set of exposed optimization is fixed and built in. So as soon as you need some other kind of optimization, you're in trouble because these compilers are not easily extendable. And this is why we came up with the functional approach of achieving high performance. And in general, we follow this same decoupling. So we have a functional data parallel language called RISE for expressing computations. And we have a separate functional language called Elevate for expressing optimization strategies as compositions of rewrite rules. And those two are the input to our compiler, and we then rewrite the input program using the optimization strategy, generate a low-level program from which we then eventually generate high-performance code for a particular architecture. And in the following, I'll briefly explain a few more details about Elevate. So how do we encode optimization strategies? And the key abstraction or the key concept in Elevate is what we call a strategy, and that is simply a function from some program P to what we call a rewrite result. And the rewrite result simply encodes the success or failure of the application of a strategy. So a simple example for a strategy would be a rewrite rule. So for example, we could encode the typical map fusion rule as an Elevate strategy for RISE programs, as you see on the bottom left. And this strategy simply says, whenever you see a RISE program that has 2 consecutive maps, you can successfully return the fused program. And in case there are no 2 consecutive maps, well, then the strategy or the rewrite rule is not applicable and we return a failure. And using the combinators Elevate provides, we can take these simple rewrite rules and compose them to build more powerful strategies. So for example, the sequential composition operator takes 2 strategies and applies both in sequence, one after each other. Or the left choice operator also takes 2 strategies, but only applies the second one in case the first one fails. And these are the kind of building blocks we use to build more powerful strategies from simple rewrite rules. The last thing we need to be able to specify is the location in the AST where we want to apply a particular rule. So for example, here we see a RISE program that contains 3 maps. And if we would now like to apply that map fusion rule, we have 2 possible locations for applying that rule. And in order to specify where we want to apply that rule, we have these what we call traversals. And I'm not going to go into the details here, but I'll just give you an intuition. And one of the things we define are generic tree traversals, for example, top-down and bottom-up, which kind of traverse the AT in a natural way and apply the given strategy at first location where it's possible. Or another useful strategy is the normalization strategy, which applies a given strategy as often as it can, which allows us to define common normal forms such as beta-eta normal form, where we apply beta reduction, eta reduction as often as possible, which is quite helpful for ensuring a certain syntactic structure during optimization. And using those building blocks, we then had a closer look at TVM's tutorial where they had these 7 different schedule programs for 7 different optimized versions of matrix multiplication. And our goal was to implement an associated Elevate strategy, which implements the same optimization, but in a way that avoids the drawbacks we just briefly discussed. And I'm also not going to go into the details here. I'm just going to show you kind of what it looks like. So here, for example, we already see a clear separation between the computation side and the optimization side with RISE and Elevate. And the Elevate strategies are composable and very explicit, whereas on the other side, we have some implicit behavior going on. And we go through all the versions in the paper. And one thing I want to highlight is that since we're using a standard functional language, we can also define our own abstractions. So for example, here, we define a simple loop perm function, which is reused in the most optimized version, which you see here, for example. Whereas in TVM, since it's kind of a more ad hoc approach, we always have to start from scratch writing these schedules. And there's no clear separation between these, as I said. And what we did for evaluating this is the first thing is we counted the number of rewrite steps we performed when we applied an Elevate strategy to a RISE program. And we found a surprisingly high number of rewrite steps, which is nice because, as you saw, the Elevate strategies themselves only cover a few lines of code, but they hide lots of rewrite steps that are hidden in this abstraction, which means that Elevate is still easy to use, but built of very simple building blocks. And more crucially, what we also observed is a same trend in performance across the different versions, which means our strategies were able to encode the same kind of program transformations which TVM describes in its scheduling API. And as I said, this is just a teaser. More details will be presented next week at ICFP, or feel free to check that out online. And thanks for your attention. And I saw there was a question. Notoriously hard to type such rewrite rules. are they typed in your system? No, in the current implementation of Elevate, they are not typed, because you're right, they are notoriously hard, although there is another PhD student of a group who writes a new kind of implementation of Elevate, and he uses some row polymorphic type system to type the rewrite roots.
Any more questions?
Of course, I can post the link of published stuff in the Slack of SPLV. That's all right.
Okay, so let's thank Bastian. And next, I think, is Cristian.
Yes, I think there's another question.
Okay, one sec. Let me answer that one real quick. People with these traverses that they sometimes have unexpected bad performance, and bad performance, like, so in general, the rewriting all those steps took less than 2 seconds per benchmark. So traversing the AST doesn't take much time. So that was no bottleneck. And if you mean performance in terms of the generated program, well, that depends on the strategy, right? Because you have to be very explicit, and Elevate just performs what you specified. And if you specified program translations do not lead to a good program, well, then of course you don't get good performance. So I think if there are any more questions offline in the Slack.
So, hi everyone, I'm Cristian Sottile. I'm a PhD candidate from Universidad de Buenos Aires in Argentina. This is my first year, and I will be talking about polymorphic system I, which is my ongoing work. So, I'll begin by telling you what system I actually is. It's been introduced by Diascaro and the WEC. It's a simpleton calculus with pairs where all the isomorphic types are identified. So, for example, these two known isomorphisms, which are the carry and the commutativity on pairs, gets to be an equivalence on types, and together with this typing rule that says that whenever two types are isomorphic, are equivalent, any term that has type A also has type B. Now we can type, for example, this term, where you can see that it is an application where arguments are actually passed in the inverse order. And this makes sense because of the purification, then commutativity, and then purification again. But now reduction gets broken, right? Because we see that this will lead to replace the variable x, which has type A, with the variable c, which has type B, and that's obviously wrong. So what we do to fix that is to add an equivalence on terms. And now, for example, a function that takes a pair as an argument can be turned into a function that takes two arguments, which were the elements of the pair. So we have to fix also the beta reduction, because even though I can transform this term into a well-formed term, the correct term, this reduction can happen. So we restrict beta to only be applicable if the argument of an application has the same type as the variable of the abstraction. And you may say, okay, but, oh, sorry, we have an example. We can see the previous term, which was the application with the arguments in the inverse order, via the carry equivalence gets transformed into this other application with the pair, and then via commutativity can be transformed into this other application where terms are in the correct order. And then via clarification again, we get a correct term where arguments are passed in the right order. So you may, okay, but why would we want to do it? Well, let's take the Carry isomorphism again. Let's say we have the function f that has type a product b arrow c, and we know we can transform it into a function f prime, which has type a arrow b arrow c, and from a computational meaning point of view, we can see they actually do the same, because this function f knows how to compute a c from two values a and b, and this function f also knows how to compute a c from a function a and b. I'm sorry, from two values a and b. So these two functions share the meaning, and that's what isomorphisms on types actually captures, right? The similarity of meaning of its terms, its programs. But what happened is that they can be combined with the same set of terms. For example, f can be combined with a pair, right? Can be applied with a pair. And f prime can be combined with two separate arguments, because, for example, it will be syntactically incompatible to combine f with two arguments or f prime with pair. And what we propose is that since isomorphisms capture this computational meaning similarity, to allow these traditionally incompatible meaning-based constructions, such as passing to f two arguments or passing to f prime a pair, and to be able to do this, and this way the programmer can focus on meaning of programs. This is something we can safely do because we know how to make them compatible, right? We know how to transform this f prime, for example, into a function that can be applied with a pair, and we also know how to how to transform, sorry, this f to be able to apply it with two arguments. So some previous results are the implementation of System I by Diaz-Caro and Martinez Lopez, where they added the fixed point operator to have recursion. They took the terms equivalence relation and make them a rural relation by directing rules. And they added some rural rules to have progress, in particular the partial beta that allows to apply a function of pairs only given one element of the pair, and late beta that allows to jump over an abstraction of a variable when I have an argument that is not actually the same type as that argument. Another is progress in System I, which is under review right now by Diaz-Caro and Dweck. Original System I didn't have progress because, for example, this term, when I passed one argument and not the two arguments in the reverse order, is stuck. But they realized that delayed beta results can be achieved actually with eta expansion, because this term eta expands to this term, and then through equivalence and through beta reduction, you have the same result of delayed beta, and that makes System I to has progression. And also the untype distributed lambda calculus, where we know lambda calculus with pairs has clashes, right? For example, we can try to eliminate an arrow, but that's not the last construction we introduced. In this case, we introduced the pair, and then we want to eliminate an arrow. And this case the same. But when we take this term equivalence from system I as rewrite rules, we get that these terms become the introduction and this other term becomes this introduction. So clashes are no longer stuck, and we have regression in the untyped lambda calculus with pairs. So now I'm going to tell you about my actual work, which is polymorphic system I, which is something I started for my master's thesis. Extension of system I to polymorphism, where we add the system F constructions from terms and types, and we add to the equivalence relation and types the isomorphisms related to the for all construct. And we also, of course, add an equivalence on terms. These are actually two examples. There are more equivalences. And we proved sexual reduction, which wasn't a trivial proof because of the amount of type equivalence introduced by the equivalence on types, because it's a congruent relation, right? And we are now proving its normalization, which is a non-standard proof because we don't have neutral terms here, because this term, which is neutral, can transform into this other term that isn't neutral. So we can't rely on that technique, and we are adapting system I's proof. So the future work is actually my PhD thesis, which I started in April this year. The first thing to do is to prove progress, which as I we plan to do, but by adding ETA expansion. Then to add some connectors like unit, top, bottom, and then to implement polymorphic system I. It may be like system I's implementation, which was in Haskell, or maybe as a GHC extension, or maybe as a library or core extension for theorem provers such as Agda or Coq. Well, that's all. I'm sorry, I didn't put the thanks slide, but thanks.
My presentation is about a recent paper contributed from my PhD thesis entitled Model-Driven Approach to Runtime Verification of Self-Adaptive Systems. I work on self-adaptive systems and targeting the runtime verification issue, addressing approximation at runtime. Two things are important in my presentation: the efficiency of the approach and the accuracy. At first, I start by an introductory slide. The work contributes to cyber systems. The cyber physical systems face fluctuations at runtime with changes coming from either the cyber part, local system, or the environment, and the cyber physical systems must deal with the changes within themselves or from the environment autonomously. Two stages for handling the changes are important. The first is monitoring, detecting the changes from the environment or any other part that affect on the system, and analyzing the updating states using rigorous techniques like verification, runtime verification, against a few quantitative properties. The main issue is that the system works in a dynamic environment and the model is changed. The model of the environment and the model of change. So referring to Marta Kowiatkowska's paper, to the software is increasingly expected to adapt to the changing demands of workload. Not only the workload, but any changes coming from the environment, but the main issue is the workload change. So self-adaptation is a major requirement in the context of physical systems. The self-adaptive systems are composed from three different parts or components. A local system that we can match it to several parts of physical systems. A control feedback loop that is responsible for monitoring, analyzing, planning, and executing the new configuration against the change from the environment. We refer to local system as the managed component, and the environment, the third part, that that can be mapped to physical part inside physical systems as unmanaged component that can affect on local system, and the changes coming from the system will be monitored and analyzed, and any appropriate action will be issued against those changes. We need to react to change proactively. It means that adaptation actions may have latency, and the system must be latency aware, and the adaptation decisions must be made in advance, as depicted in this slide. A lookout horizon will be analyzed, monitored, and analyzed for this purpose. The model of self-adaptive system is the composition of the environment model and the local system model. The output of the verification or analyzing is presented as a form of alpha, a subset of actions or adaptation actions, and a U that is total utility or maximization of the utility of the system in a lookout horizon that I presented in the previous slide. Some quantitative properties, the system is verified against some quantitative properties. For example, the robotic arm will execute an emergency stop when the probability of collision within the next 3 workflow steps exceeds 80%. We have an example that I skipped by now. Okay, the main problem of the research is runtime approximation. Why runtime approximation? Because of size of the model, the outstanding is city space explosion problem, configuration, timing restriction, the restriction for decision making, variability of the model, that the model is that we face a variable model at runtime. We use epsilon approximate by stimulation technique for approximating the main model composition, the composed model of the system. System model with approximation is like that the changes are coming from the environment and are monitored from the environment and added to the parametric model as a set of parameters and sent to approximation verification engine for verification purposes with some quantitative properties. The main idea is to divide the model into a set of SCCs, strongly connected components, apply epsilon approximation to each SCC independently, processing each SCC independently, propose an aggregation algorithm for summing of the verification in each component, and efficient updating mechanism. We find a certain upper bound for errors of approximation, and we proposed a sketch of proof for theoretical aspects of the error band analysis. We proposed average error band as an appropriate upper bound for errors, applying by epsilon approximate calculation. Our result in terms of efficiency proves that the decision-making time will be decreased after 8 and 9 step of make controlling loop, and the time the decision-making time is decreased drastically. Average decision-making time is decreased compared to other related work. Accuracy of we define the accuracy of decisions by this equation, and evaluating the accuracy of the proposed system with respect to the previous metric. The system has a reasonable accuracy with different levels of reduction approximation. As a conclusion, the self-adaptive system needs runtime verification to deal with efficiency issue. We use strongly connected components to divide the model into its SSCs. In each round, only those SSCs are subject to change, only to be reapproximated or re-verified. We proposed an upper bound for approximation error and proved it theoretically. The results show that the validity of the approach in terms of accuracy and efficiency. Selected reference as this slide. Thank you. If any question, I would answer.
I'm James Wood, a PhD student at Strathclyde, so one of the home people to the summer school. And today I'm going to talk about some work I did last week because it seemed kind of fun on customizing bidirectional type checking. So I'll get my pointer on just so that's there. Bidirectional type checking has like quite a lot of uses in I guess type theory. It's been around since 1998, so kind of established, but not necessarily like massively old idea, and it's still kind of being picked up. And the sort of first thing is to distinguish between types that terms that synthesize their types, so like a kind of inference process, and terms that are checked against a type. So the type is known beforehand, and that helps us check the term. And some checkable things in a standard bidirectionally typed language include constructors, like data constructors. So when we want to type a nil or a cons for a list, we'd already know that we were trying to check a list. And similarly for environments, and this allows us to do overloading of constructors. So we could either be in the situation where we know we're making a list, and then we see a nil, and we go, oh, that's the nil list, versus we know we're creating an environment, and then we, well, first we need to know that it's an environment on the empty list, and then we know that this nil means a nil environment. So this is actually even happening in this definition right here. So environment takes a thingy and then a list and produces a type. So we know that this at the end must be a list. And this is list cons, but we're actually defining env cons. So it's kind of nice. And we can use this in terms. The game here is that these green things, like defined functions, or this is not a function, but defined things, have to be annotated with a type, and later we'll use that type. They will synthesize their own type, and it'll be exactly this env of all this stuff. There's a bunch of overloading going on in this. That's a nice term. This is supposed to be a kind of substitution between the context A and B and the context A, comma B, for those that will follow that through. Everything in the types here is list-like. Env takes a thing in a list, but in the inside the definition, these things are being checked to env type. So that works pretty nicely. And now I'm going to break it. This is a kind of, people normally would define vectors a bit like on the previous slide, but now I've defined, so this is a list with known length. I've defined that as basically a function from indices. This is the finite type with n elements to elements. So that's a definition of vectors that you sometimes come across. It's sometimes useful, and we can kind of start showing that they're similar to normal vectors. So we've got a empty vector of length 0. You've got this funny syntax to define it, and cons takes an element and sticks it on the front of a vector of length n to make a vector of length n plus 1, successor of n. Does that by is the fin the first one 0 or the later one, and gives us the result like that. This is all quite nice, but if we'd type checked it with lists and environments already in scope, Agda would not be happy. It would say, these names are already defined. And even if we did manage to keep them out of scope for the definition, but later have these vec pseudo constructors in scope, in the old example, it'd go, oh no, I don't know what to do on all these things because green things synthesize their type based on the type we gave them, but it could be the red things from before, so it's all kind of breaks. The kind of usual way around this in Agda is to sort of have this vector stuff in a module and import it with a qualified name. But I don't like the qualified names. They kind of make the code ugly, and bidirectional type checking sort of promises that we only give type annotations at this kind of outermost level, and they are kind of, I mean, qualified names I see as a form of type annotation, so that's bidirectional type checking sort of failing at its own criteria. So what can we do to fix it? Well, what do people normally do to fix these kind of things? There's these ideas like in Java or languages like this. Overloading's a kind of common thing, and it seems to be done for sort of any members of classes or whatever. And I'm going to say that this is the sort of blank canvas I paint on in this talk. It's kind of you should think of it in the same way as we have these names, and they are distinct things, but we dispatch based on types. But I've never seen the sort of bidirectionality taken seriously. I think these languages usually do a kind of everything can infer its type because it's already had a type annotation. Meanwhile, I guess something we're not going to do is something like Haskell style type classes, because somehow it's two typed in a way. So this f, if you do the obvious thing to try to get some overloading, then f is going to be a type to type thing. But then in the previous slides, we cared about things like that were indexed by a natural number or indexed by a list, and the thing would soon get very complicated. If someone can get this to work, I'd be kind of pleased, because then Haskell could be a bidirectionally typed language. But I don't think even things like functional dependencies get you really there. Okay, so let's have a look a bit more closely at what's happening in a bidirectional type system. It's based on having two judgments. Either we know the type and check against the term, or the term synthesizes its type. And in these constructor cases, everything is checking. So we know the thing's a list. That means we pass that type into here and pass the type into the tail. We destructure this list for the environment, pass that on through. But when we define the function, that's saying it's synthesizing its type. It's going to give us the type that it said it would at the definition point. And you can kind of see disharmony or whatever here, in that if this was a cons, then you're kind of synthesizing and then trying to check. And what we want to do, maybe it's evident now, is to make this also a checking form so that we can dispatch on it. And what I'm going to do now is switch to this Coq prototype I've got working. In Coq is basically nicer to write tactics. I tried out the LP language, it seems to be quite nice. And the idea of this is we're going to have one tactic, cons, and that's going to unify the type we're given with something that has a cons, like list, or unify it with vector of a successor length. And it's going to say, okay, give into the goal, or whatever they call it, the right cons, either cons for lists or cons for vectors, and fill in everything we know. It's already going to be applied at type A, and we know the length in the vector case. And this gets used as in a tactic script like this. Unfortunately, this isn't massively readable, but I use exactly the same overloading principle in a comment here to write out this is a vector of lists, and the script kind of shows you use cons and nil just when you see them in the goal, and it works out. And some other things I've implemented is we can do pseudo eliminators, so we can overload lookup based on synthesizing a type here. And map's an interesting one. It checks against function type. That seems to be the thing that works. And future work is to actually put some more work into it, and also improve the software engineering of it, because everything has to be in scope at the moment. That's a bit bad. And put it to a language I actually want to use, and see what else there is to try out. So thanks for listening.
Thanks a lot. There's questions in the chat.
Someone says, I've never used this LP tactic. What do you like about it? I don't know. I've never used Coq tactics before, really. So this is my first try. LP seemed quite nice because you get some useful things like here I'm using an LP variable. LP stands for LP. An LP variable A. So this is a bit like, well, this is lambda prolog. So you get a prolog variable that's going to unify with stuff in here. And then that can be reused in kind of the Coq quotation. Maybe the usual tactic languages have something like this, but I mean, it seemed like a nice. It seems like a nice way to do tactic languages. This try to unify things, possibly fail, and go to the next case, and yeah, they got me going pretty quickly anyway. So I like that.